let's go and check example when not linearly independent. So the vectors now are going to be linearly dependent. Let's try this set. Okay. So we have the check goes like this. We suppose that A110 plus B101 plus C211 equals 0, 0, 0. Okay? Then we can immediately write down the augmented matrix for this linear system is and we're going to solve with Gauss's method, minus rho 1 plus rho 2 to get 1, 1, 2, 0. And minus 1 time is 0. And then we're going to have minus 1. And minus 2 plus 1 is minus 1 and 0, right? And then we're going to have 0, 1, 1, 0, right? And then we can do rho 2 plus rho 3 to get 1, 1, 2, 0, 0, minus 1, 0, and then 0, 0, 0, 0. Okay, so we have an infinite number of solutions because we have a free variable. An infinite number of solutions. Okay, that means that we know that it's going to be linearly dependent. So, but how do we sort of conclude, apart from just what we do is we want to come up with a counterexample. So what are these? We should write out the equations here. The equations are going to be minus, this is the A, B, and C column, minus B plus minus C equals 0. So that means that B equals minus C, right? That's just rewriting this. We have this is one equation. And the first equation is, I'm doing back substitution, is A plus B plus 2C equals 0. And you can see that A and B are leading. So we're gonna write them as in terms of the free variable. So we want to eliminate B. Since B is minus C, this equation is going to become A plus C equals 0. So A also equals minus C. So if A is equal to minus C and B is equal to minus C, this will be true. So what we want to say, since C is a free variable, we can choose, our goal is to find counterexample. Once we know that it's not, when we know it's not linearly dependent, you could stop there, but what I want you to do is to actually exhibit an example of linear dependence. Because you want to go, this is a exhibit case of linear dependence. There can be lots of different situations, but you only have to demonstrate one. Okay, well, that means let's choose. The simplest one here would be C equals to -1, because then A equals B equals 1, right? And then, if we go back up here, we can see, right, that we have 1, 1, 0, that's A equals 1, plus 1, 0, 1, that's B equals 1 there, minus, that's the C equals 1, 2, 1, 1, equals 0, 0, 0, right? So here's the case. See, so we have this, so we know this is, and you can check that it's true, right? First of all, 1 plus 1 minus 2 is 0, 1 minus 1 is 0, and 0 plus 1 is 0. In fact, you could write then 2, 1, 1 equals, by adding it to the other side, equals 1, 1, 0 plus 1, 0, 1, which is how I constructed the example in the first place, by choosing a third vector to be the sum of the first two. But this is how it plays out, so that we can see these vectors are linearly dependent. I mean, formally, you would, logically speaking, you could stop up here with a free variable and infinite number of solutions, therefore they're linearly dependent. But like on a homework problem, I'm going to ask you to find a counterexample, because you could choose C equals to 0. But if you find a counterexample, then you're actually exhibiting a case of linear independence that sort of emphasizes the educational point that yes, this abstract thing really did lead to linear dependence. So the goal is you start from the same process of supposing the linear combination is 0, solving the linear system, and if there's one solution, you're home free. If there's infinite number of solutions, you pick one that's non-zero and exhibit a linear dependence. And so you've exhibited that are linearly dependent. And that's the whole game. And if you look at, I think, the regex problems on linear independence, this reviews, right, chapter 5. I'm not sure if hopefully these page numbers, I don't know if these page numbers are exactly correct now, because I keep revising the text. But so here's the concept, right? Here's this test, premise, consequence. So we have to show this. How I use this test, this goes through abstractly what we just went through. Assume the premise of this implication. The premise is homogeneous linear systems, can solve for the numbers up here. Okay, if there's one solution, it will be the 0 solution, and they're linearly independent. If there's more than one solution, there are many non-zero solutions. Choose one. That's our counterexample. There'll be a choice of non-zero numbers, which makes the premise true but leaves the consequence false. Therefore, the test implication is false, and you know that then, P plus Q is not true. Therefore, the subset's linearly independent. So the problem is, I give you a set of vectors and go through the argument, and here's a lot of steps, and then write out the solution set here, and you're supposed to write in here one of these justifications of each step. So it's just a matter of walking through and understanding the stuff that we just did. Then the homework, I'll actually ask you to demonstrate that these certain vectors are linearly dependent or independent. And all of these regex exercises, see, example 2, example 3, example 4. Here's one with polynomial vectors. So we have to think about that. And here's example 4 with matrix vectors. So it doesn't depend on what the vectors look like. You have the same idea of linear dependence and independence. So this is the central sort of thing that's going on there. Okay,